All of you, welcome to the session. Today we are going to talk about Joule-Kelvin effect. Okay, let us see. When a gas under a constant high pressure is passed through a porous plug to a region of constant low pressure, there is a change in its temperature. This is named as Joule-Kelvin effect or Joule-Thomson effect. Let us see once again. When a gas under a constant pressure, see there, at a constant high pressure, initially gas is at a constant high pressure. If it is passing through a porous plug, if it is passing through a porous plug to a region of constant low pressure, see there, where the gas is passing from high pressure region to low pressure region through a porous plug. So what happened? So it may be cooled down. That means there is a change in its temperature. This is named as Joule-Kelvin effect or Joule-Thomson effect. Okay. So next point is all the gases when passed through a porous plug, when all the gases when they are passing through a porous plug suffers a change in temperature. You have to concentrate on at this point. All the gases, whatever the gases we take, when they are passing through the porous plug, they suffer change in temperature. That means there is a change in temperature. At ordinary temperatures, all gases, at ordinary temperatures, all the gases except hydrogen and helium suffer a fall in temperature. That means the gases are become cool. Okay, so the temperature may down when it is passing after passing through the porous plug, except hydrogen and helium. That means they suffers cooling effect, while hydrogen and helium suffers a slight rise in temperature. That is what heating effect. See there, when the hydrogen and helium both are, when they are passing through a porous plug, their temperature slightly increased. So that effect is called heating effect. When the temperature of other gases, when they are passing through the porous plug, so the temperature decreased. That is what called cooling effect. Okay, next point. The change in temperature is directly proportional to the pressure difference on the two sides of the plug. See there, so the change in temperature is directly proportional to the pressure difference on the two sides of a plug. Next point is, as the initial temperature of the gas rises, see there, as the initial temperature of the gas rises, the cooling effect diminishes. The cooling effect diminishes at a certain initial temperature known as inversion temperature. The cooling effect is changed into heating effect. The cooling effect is changed into heating effect. So these are the completely theoretical explanation. Let us see what expression for Joule-Kelvin effect and where we can find the equation for coefficient of Joule-Kelvin effect. So let us see what is that. Expression for Joule-Kelvin effect, or else we can write coefficient of Joule-Kelvin. Coefficient of Joule-Kelvin. Coefficient of Joule-Kelvin effect. Right. See, when the gas suffers Joule-Kelvin effect, its enthalpy becomes constant. Okay, then we know that how can we write enthalpy? Enthalpy can be represented by H equal to U plus PV. H equal to U plus PV. Okay, now what happened when the gas suffers Joule-Kelvin effect, it will become constant. Write down, that is equal to constant. Okay, now, so let us take differentiation on both sides. So what happened? We take differentiation, so where h is constant and d of u plus pv equal to what? We know that 0. Differentiation of constant is equal to 0. Then what do we get finally? We get there du plus pdv plus vdp, right, equal to 0. Equal to 0. Right. So let us assume this is what equation number 1. And according to thermodynamic first and thermodynamic second law, we know that dq equal to du plus pdv, right? dq equal to du plus pdv. Assume this is what equation number 2. And thermodynamic second law can be what in terms of entropy, dq equal to pds. So this is what 3. Let us make 2 equal to 3. Understand, then what we get there? TDS equal to du plus PDV. TDS equal to du plus PDV. Assume this is what equation number 4. Substitute 4 in 1. Substitute 4 in 1. So what we get there? Finally we will get there. So if you substitute du plus PDV where TDS, then what we get there? We will get there TDS plus VDP equal to 0. So assume this is what equation number 5. Understand, equation number 5. Now here what we have to do, let us take S is a function of entropy is a function of pressure and temperature. Entropy is a function of pressure and temperature. And taking differentiation, what we get there here, partial differentiation there, dou S by dou P, differentiating partial differentiation with respect to pressure at a constant temperature T dP. Here it is dou S by dou T at a constant differentiation, partial differentiation with respect to temperature and where the pressure is constant dP. Assume this is what equation number 6. Okay, now substitute equation number 6 in 5. Substitute ds value in 5. Let us see what we get here. Now, so I am substituting ds value here. We get the T into, and the ds value is dou S by dou P, constant temperature into dP, okay, plus multiplying with T here T and dou S by dou T, constant pressure P and dt equal to 0, right? Sorry, plus here VdP equal to 0. Understand? Now, so what we have to do here? So we know that where this term T dou S by dou T P can be written as T dou S by dou T, okay? So at constant pressure P, and this can be written as dou Q by dou T P. This is what specific heat capacity at constant pressure, that is represented by Cp. That is represented by Cp. And one more thing here, according to Maxwell's thermodynamic equations, see there here dou S by dou P T can be written as here dou V by dou T. Here it is constant pressure, we'll get their minus. And substitute these both equations in this above equation, See there what we get finally, we get there here you have to, T is there, T, and this value is what? Minus dou V by dou T, constant pressure P, and here it is what there? Here we have dP, and plus it will be T, and here it is what? Cp dt plus VdP equal to 0. Now what I am doing here, see there carefully. What I am doing here, so here what I am doing, T Cp dt equal to, I am sending these two terms on the right side and take dP common. Therefore what we get there finally, we will get there T and dou V by dou T, constant pressure P dP, and minus VdP. Alright, so take dP common, then we'll get the T Cp dt equal to and T into dou V by dou T at constant pressure minus V, here it is dP. So from this equation, I'm going to adjust this equation like this. So dt by dP equal to dt by dP equal to, here it is, here we get there. Sorry, here we have no T here. Alright. Right. So from this equation, dt by dP equal to, so 1 by Cp into T into dou V by dou T bracket P minus V. So this is our required equation. So here we have to put there H. So what it represents? The ratio at constant enthalpy, the ratio between change of temperature to the change of pressure is defined as coefficient of Joule-Kelvin. Okay, see that at constant enthalpy, the ratio between change of temperature to the change of pressure is defined as Joule-Kelvin coefficient. Joule-Kelvin coefficient that can be represented by mu, where mu equal to dP by dP at constant enthalpy equal to 1 by Cp into T dou V by dou T at constant pressure minus V. So this is the expression for Joule-Kelvin effect. So let us see a few terms here where if mu is positive, that means there is a cooling effect. If mu is positive, mu means mu equal to dt by dP H is positive, then there will be cooling effect. And if mu equal to dt by dP H is negative, there will be heating effect. Heating effect. When mu equal to dt by dP H equal to 0, then what happens? So is 0, there is neither cooling nor heating effect. This temperature is known as inversion temperature. Neither cooling nor heating effect. So therefore this effect is called inversion temperature. This temperature is known as inversion temperature. This temperature is known as inversion temperature. Okay, so this is what coefficient of Joule-Kelvin effect. Okay, right.